In this video, we're going to go over the Moore Terrain Derivatives tool. Ian Moore developed several secondary topographic attributes. Secondary topographic attributes combine two or more primary attributes, and primary attributes consist of derivatives from an input DEM, such as slope, flow accumulation, curvature, or upslope contributing area, and there's many more. But by combining these primary attributes, our ability to understand the landscape characteristics that involve hydrology and geomorphology or ecology are greatly enhanced compared to what can be gained from looking at just a single attribute. The Moore Terrain Derivatives tool spits out one primary attribute, and that's a specific catchment area, which is calculated using the D-infinity method. Unlike the D8 flow direction method, the D-infinity is a more advanced flow writing algorithm. The D8 method routes water from one cell to only one neighboring cell, while the D-infinity approach, which was developed by David Tarbotton from Utah State, allows flow to be proportioned from one cell to multiple downstream cells based on slope angle. This approach allows flow to diverge or converge, whatever the landscape is naturally telling it to do. So, using the D-infinity method, a specific catchment area grid is generated, which is the contributing area per unit length. In our case, length is the grid cell size of 2 meters. The Moore Terrain Derivatives tool also generates two secondary topographic attributes, the first being the stream power index, which is a measure of erosive power of flowing water. And this is found by taking the natural log of the product of the specific catchment area and the tangent of slope, and in this case, slope being beta. And then the second attribute is topographic wetness index, which predicts zones of saturation where the specific catchment area is typically large and slope is small, which makes sense according to the equation, which is the natural log of the specific catchment area divided by the tangent of beta. Again, beta is slope. If this is the first time that you're hearing about D-infinity or secondary derivatives like the stream power index or topographic wetness index, or if, say, you've heard of them before but aren't very comfortable, please not use this as your only source of information. Feel free to go to any of these other sources I've provided on this slide to read further into them. It'll really benefit you to understand how these work and how they should be interpreted, especially understanding them further than I'm going to go into in this video. So, thank you. When running the Moore Terrain Derivatives tool, a DEM is required, and it's up to the user whether you want to use a filled DEM or an unfilled DEM. If you use a filled DEM, that means that the sinks in the landscape have been filled, and therefore flow paths are going to go straight through depressions. This is going to result in higher flow accumulation values and therefore a higher stream power index. If you use an unfilled DEM, flow paths are going to end at each sink or depression, which therefore results in lower flow accumulation and a lower stream power index. These results are going to be used in later tools such as the grass waterway siting, so depending on your landscape, if you know it has a lot of depressions or is very pocky and that you won't site grass waterways through there, it may make more sense to use the unfilled DEM. However, if you're really unsure, the filled DEM is probably going to be your desired choice. As you'll see in later tools, you will have the option to account for the presence of depressions. But it's completely your call. You could also run both and just use a different name in the outputs. Briefly, I just want to show the difference in results of the grass waterways tool compared to when using a filled DEM to derive these terrain attributes to when you use an unfilled DEM. In this particular watershed, there are many depressions, so using the unfilled DEM automatically reduces the amount of grass waterways because the stream power values will be much lower within that grid compared to when using a filled DEM. Alright, so we're in our map document. Let's go ahead and run this tool. So we open up more terrain derivatives. You can see we have two inputs, a DEM, filled or unfilled, and then our slope raster. We're going to get those three outputs of specific catchment area, the stream power index, and our topographic wetness index. So for the DEM, I'm going to choose to run this with my filled DEM. As we went over, this is totally your choice. The tool help over here provides the same details that I went over. Our slope raster is automatically input, and then these three outputs are automatically populated. However, I like to add the name of the DEM that I chose to use to these outputs, mostly just for record keeping. Sometimes I run this twice to see the difference in my grass waterway output later on. So I'm just going to add a little underscore fill after the base name. Remember that we always want to end our outputs in that 12-digit huck, so that's why I'm inserting it right here. So now everything looks good to me, and I'll hit OK and let it run. Alright, so the tool just finished running, and we have our three outputs automatically added to the map doc. We have the wetness index, the stream power index, and then the specific catchment. So first off, let's look at the specific catchment area output. So again, the specific catchment area is a measure of area per unit length. So for us, that's 2 meters, which is the cell size of the DEM used to derive this. So let's do some symbolization so we can see a bit more. Similar to our flow accumulation raster, it's pretty bland at first. Since it's similar to the flow accumulation raster, we can go to classified. And we're going to use those two classes again. So breaking down to 2, we'll hit classify. And in this case, if we wanted to see concentrated flow of at least 1 acre, I'm going to input 500 as my cell value. Remember, previously we entered 1000 when symbolizing for the flow accumulation grid, and since the specific catchment area cell values are area divided by the cell width of 2 meters, now 1 acre of concentrated flow is equivalent to 500. Alright, so we've added some color, or we've classified, so now let's add some color. So I'm going to make that see-through, and we'll make this yellow. We hit apply, OK, and now we can start to see these areas that have at least 1 acre of concentrated flow. If we look at it with our hillshade underneath, you can see it does make sense where these areas are. On to the next one, stream power index. Already you can see there's a lot of detail to this raster. Let's add some color to it. And we'll hit apply, OK. And with this we can really start to see where flows are converging and diverging. So in areas of pink to this darker blue is where we have high erosive power. And it makes sense that this does coincide with our stream reach, which you can see overlaid right along that dark blue color of the stream power index. That makes sense. We have our incised channel there, which would coincide with a very high stream power value. Alright, so now let's take a look at our topographic wetness index grid. So I'll turn it on, and let's add some color. Go with this scheme. Alrighty. I'll just choose an area to zoom in on. Okay, so with this scheme, areas that are in teal to this darker blue are areas of saturation. Here, the specific catchment area value was high, but the slope was lower. And this results in slower moving flow, allowing it to saturate an area, like along a floodplain or throughout an alluvial fan. In the brown areas, we have steeper slopes and therefore less opportunity for soil saturation. Here's a brief recap of the more terrain derivative tool. These results are going to be used in later tools, so be aware of which input DEM you use to calculate these.